While I put up the outline of my talk for you to look at and ponder over, I'd like to ask you a couple of questions. Who has heard of measurement uncertainty? Quite a lot of you. Who has used measurement uncertainty in their work? A surprisingly large number. I'm very pleased about that, yeah. And so I don't have to go too basic, I don't think, in this talk. It's for you to judge. I'm going to consider direct and indirect measurement and the measurement model, explain what that is. I'll give a simple example of a spring scale. I talk about the fact the measurement is imperfect and the number after the mysterious plus or minus sign you see in a lot of documents. I mention probability and the coverage factor. I mention the concept of uncertainty propagation and the GUM, that's the International Bible on measurement uncertainty. I mention a topic quite close to your heart, absorbed dose measurement. And I mention again the GUM itself and a supplement to the GUM, and then conclude. We have a measured value from some experiment. We might obtain it directly or indirectly. If we obtain it directly, it might be a length measured by a rule or something like that. An indirect measurement is something like a mass measured using a spring scale. You don't measure the mass, you measure the extension. And you convert the extension to mass with some formula, with some rule, with some model. If you have an indirect measurement, you convert the quantity actually measured into the quantity required. And as I say, you use a measurement model which involves input and output quantities. The inputs are the things you know something about. The output is the quantity you want to learn about. Spring balance, for example, measures extension, and you use the model to calculate the mass. It's quite simple in this case. You have a restoring force proportional to the extension, Hooke's law. And for a mass, you have acceleration due to gravity, and so you've got the equality mg equals kx. M is mass, g is acceleration due to gravity, x is the extension, and k is a spring constant. If you know the spring constant k, you know the extension x, you know the local acceleration due to gravity, you're in a position to determine the mass on the spring balance. But there are measurement imperfections. We well know that no measurement is perfect. There might be some exceptions to that. If you have a counting process and you're sure of the counting process, you might be able to idealize that precise number of counts. But in general, no measurement is perfect. In our case, the spring constant, the extension, and the local acceleration due to gravity are not known exactly. Hence the calculated mass, m, is not known exactly. We want to know how good is that value of m. To know this, we've got to know something about the input quantities. We want to know something about x, k, and g. In this case, I'm using hypothetical numbers here. We suppose the observed value of x is 20 millimeters, and by hook or by crook, we've established a plus or minus 0.5 millimeters on that. Similarly, we know about the spring constant, 8.5 in suitable units, plus or minus 0.5. Acceleration due to gravity, 9.81, plus or minus 0.01. And so we've got some knowledge of our input quantities. What are the corresponding values of the mass, calculating using the simple formula on the previous slide, and what is the number after the plus or minus sign attached to that mass? the extension is 20.0 millimetres plus or minus 0.5 millimetres. What does that mean? It means the extension probably lies between 9.5 mil and 20.5 mil. What does probably mean? In metrology, it means something. It usually means that the probability that the extension lies in that interval, 19.5 to 20.5, is 95%. Of course, different probabilities could be used here, but it's traditional in metrology to stick to 95.5%, indeed in a lot of disciplines too. To dispel any doubt, you should always quote this percentage, which is called a level of confidence or coverage probability. You should always state that if you're using the plus or minus notation. Some textbooks mean exact limits. We know that the extension of the spring is within plus or minus 0.5. You're on dangerous ground if you say you know that. The 0.5, incidentally, is known as expanded uncertainty in metrology. Probability, a slide on probability, we can interpret as follows. The set of possible values a quantity can take is described by a probability distribution, often a normal distribution. And so you see that the picture there, normal distribution, you can see the value, our best estimate, our measured value, denoted by y. You can see the lower limit, y minus u, the upper limit, y plus u, 95% of the values between those limits. We take the standard deviation of this distribution as a measure of uncertainty. That measure is known as a standard uncertainty. The coverage factor gives us the relationship between a standard uncertainty and an expanded uncertainty. If we denote the standard uncertainty by small u, the expanded uncertainty by big U, the relation is there, capital U equals K times little u. K is known as a coverage factor, and its value depends on the distribution. It might be normal, it might be rectangular, it might be Rayleigh, it might be Poisson. You have a lot of distributions occurring throughout physics. It depends on the distribution and it depends on the coverage probability, 95% or whatever. And for a normal distribution, K equals 2 for 95% coverage. Back to the example of the spring. Let's assume, at least for the moment, the distributions are normal. And so we have our three quantities that we know about. We have x in millimetres, we have k in newtons meters to the -1, we have g in the usual units. We have the values, 20.0, 8.5, 9.81. We have the expanded uncertainty from the plus or minus statement. And we have the standard uncertainty given by those expanded uncertainties divided by k, divided by 2 in this case. And if we want to quote it, I'm going to use these, we have a relative standard uncertainty, which is the standard uncertainty divided by the value. So we can quote those two. Uncertainty propagation. We know how to obtain the value of m. It's obtained from the measurement model. In this case, m equals kx divided by g. And we plug in the numbers we started with, and that gives us a value of 17.3 kilos for the mass. In terms of propagating the uncertainties through that formula, a number of formulae are given in the GUM, which I mentioned. I'll refer to it again later. But in this case, this relatively simple case, it reduces to a very straightforward formula. The square of the standard uncertainty of m divided by m squared is given by the sum of three terms of similar form. And so we can see the relative uncertainties here all squared, like ux divided by x all squared. And so we plug in the relative standard uncertainties and we produce a value for the square of the relative standard uncertainty associated with m. Taking its square root gives the relative standard uncertainty divided by m is 0.032. And so the complete measurement result for many purposes is that mass 17.3 kilos with relative standard uncertainty 0.032. The expanded uncertainty, if we need it, is given by multiplying u of m by the appropriate k, often k equals 2. If we don't like the number we've produced, we think the uncertainty, the standard uncertainty associated with m is too big, we want to do something about it, we look at the formula, and we obviously pay maximum attention to the biggest contribution in that formula. Biggest contribution is obvious, I've indicated it here. We pay attention to that, and if we can reduce that, we'll reduce the according standard uncertainty associated with the result. I'll give an example of absorbed dose measurement. The basic formula for absorbed dose measurement is this. Absorbed dose is given by a product, a simple product, an activity time integral, which is obtained for a previous calculation, and a tabulated factor depending on the radionuclide used. The output quantity, the one about which we require information, is obviously D, the absorbed dose. So if we have information on A tilde, the activity time integral, and the activity on the S factor, we're in a position to deduce the absorbed dose. That's what I say here. In addition, if we know information about the uncertainties associated with A tilde and S, we'll be able to produce the uncertainty associated with D. It's a difficult problem. It's superficially simple. The absorbed dose is a simple product of A tilde and S. If we look at some candidate methods for estimating A tilde, which remember is an area under a curve, an integral, for some whole body retention data, we have two very different values. The values I give here, 543 and 387. And they each have associated large uncertainties. Here we see a set of values. The value to the left at time equals 0 is the administered activity. And the administered activity decays, of course, throughout time. We perform a series of measurements about every hour or two. Well, how many have we got? 7, I think, here. And so, by some means, we want to evaluate the area under the activity time curve. And so, two different ways of producing an activity time curve are given there in red and blue. Red is an approach called the peeling approach. The blue is called some form of least squares approach. And so the curves are different. And so we might expect the areas, in this case, to be appreciably different. And indeed they are, 543 and 387. And so attention to detail in providing the regression fit to that curve is indeed important. And the regression fit to that curve should also, of course, take account of the measurement uncertainties associated with the data. Another important factor is we want to find the integral under the curve. That means the whole curve, from time equals 0 to time equals infinity. And the curve itself is affected by a number of things. It's influenced by the radionuclide used, of course, but the curve is very patient-specific. Different patients respond in very different ways to therapy, and the curves can be very different. I made a study of 30 data sets provided by the Royal Marsden and the Royal Free Hospital. The patient variability could be as much as a factor of 100. So some patients absorb the dose in 30 minutes, some absorb the dose in 48 hours. And so it's very different, and so you need accurate data that relates to the specific patient. The uncertainty associated with S, it's convention to take that uncertainty, use a value for S which comes from tables. They use phantoms to create those tables. The tables depend on the radionuclide used and the form of phantom they're using. But it's much better to use a patient-specific value for S. That costs money, but it's much better, obviously, for the patient to get a value which is specific to him. We have uncertainties associated with S, uncertainties associated with A tilde, so in turn there'll be an uncertainty associated with the estimate of absorbed dose. I said this model is simple, but in practice it's more complicated. You might have additional terms in the model, correction factors and so on, so they contribute further uncertainties. How do we evaluate all these uncertainties? Well, if you can evaluate the uncertainties associated with the input quantities, and that itself is a difficult task, I've given lectures on that, I'm not going to speak about that today, but it's a propagating of those uncertainties through the model. And there's some excellent international documents which discuss that. There's the GUM itself, the one I mentioned, the Guide to the Expression of Uncertainty in Measurement. It adopts the so-called law of propagation of uncertainty. It uses the central limit theorem to decide that the measure rand, the thing you want to measure, is described by a normal distribution. The second international document I want to mention is Supplement 1 to the GUM, which is propagation of distributions using a Monte Carlo method. That takes account of whether the distributions involved in the exercise are normal, rectangular, Poisson, whatever they are. It uses the actual properties of those distributions, and so it propagates the distributions themselves rather than the uncertainties, the standard deviations I mentioned earlier. And we think it's likely to be more suitable in dosimetry because the uncertainties in that discipline can be large, as we've seen, and the models can be, and normally are, nonlinear. Okay? Concluding. I said that we rarely measure directly. We almost always have to measure indirectly. The things we observe have to be related to the things we want through a calculation, a measurement model. And I gave two examples, the spring balance and an example of absorbed dose measurement. I mentioned that the GUM works well for many calculations in physics where the uncertainties are generally small, that the models might be relatively simple. But in medicine in general, in dosimetry in particular, the uncertainties can be appreciable. And so we're going to look at the GUM supplement 1, which is the propagation of probability distributions. We think that can be used to advantage. And we've just entered a proposal for an European project. EMRP, as we heard from the previous speaker, that will investigate such things if the proposal is successful, of course. Thank you.